So it's my pleasure to introduce Sam Foreman. He's a computational scientist in the AI ML group here at Argonne, and he's a pretty integral part of the AuroraGPT project that we're working on here, and he's going to talk to us today a little bit about it. Take it away, Sam.
Yep. Yeah. So thanks. Yeah. Thanks for the introduction. Yes. So if people were here for the session yesterday afternoon, I gave a talk on large-scale distributed training. So I'm back again here now to talk about the AuroraGPT project, which is Argonne's internal large language model development project. So these slides so feel free to ask questions at any point if anybody has anything they want to ask. These obviously being lunch talk, everybody is eating, and so kind of aware that I only have a portion of most people's attention. And so this is really kind of meant to be pretty low stakes and interactive. So if there's anything anybody wants to ask or questions at any point, feel free to jump in. And hopefully we can get this done in time for everybody to finish their lunch. Sure. The slides are not uploaded, but I can send the URL in the Slack channel. Slides. These are the right ones? Yes, it seems to be. Okay. So yeah, I just sent them in the slides channel. Hopefully the right Slack, yep. So feel free to follow along. There's URL is also there at the bottom if anybody can't get it from the Slack. Sure, so maybe a bit of background. So AuroraGPT, like I said, is Argonne's internal effort to develop and release a large language model, specifically with the goal being specifically that it will be tailored towards scientific applications. So what does that mean? So in addition to generic text-based data, the eventual goal is that it will also be trained on scientific data, which include scientific papers, scientific data from different domains, various scientific texts. So there's an ongoing effort to parse and tokenize large collections of academic papers is one major source of this additional scientific data. And as part of this, we hope to explore pathways towards a scientific assistant model, and more generally kind of investigate the usefulness of large language models in scientific development and scientific research, and trying to better understand how large language models can be used to accelerate the scientific process, discover new hypotheses, all around any new insights that are to be gained from them. And so this is very much the scientific component of this is very much exploratory, and there's been a lot of work recently, specifically on scientific assistant models, and I think it remains a bit unclear how best to utilize them in a scientific setting. One of the major problems, as people I'm sure are aware with large language models, is their tendency to completely make up facts or provide the wrong facts or just generally be unreliable in terms of factual-based information. And so trying to reconcile that with scientific data where there is a source of absolute truth is definitely a very active area of research, and something that we hope to get a better understanding of from this. So this is so the AuroraGPT project is the Argonne specific project with the goal of building, training, and releasing these large language models. As part of this, which is also kind of nested within this trillion parameter consortium, that you might have also heard about. It's really kind of a larger international consortium with the goal to incorporate foreign languages and figure out ways to best incorporate text and data from different languages. And so we're working in collaboration with Riken in Japan, Barcelona Supercomputing Center, and as well as other supercomputing centers from other language-speaking countries. And so as part of this, we hope that the eventual model release will be both multilingual and multimodal. So we initially plan to target English, Japanese, French, German, and Spanish. And as far as languages, and for multimodal, we plan to target images, text, as you would expect, as well as scientific tables, equations, proofs, time series, graphs, all of these different data types that are common across scientific disciplines. And so that is very much an active area of research, not even for just our group, but I think within the larger community, finding ways to effectively tokenize non-standard data types is, kind of an open question, I think. And so maybe the last thing I'll say on this slide, at the bottom, we have a very rough timeline of when we expect these models to be released. So in this spanning 2023 to 2024, we've focused primarily on text-based models. Looking forward into next year, we plan to incorporate multimodality and work towards releasing a fully multimodal model. And then eventually, with what we've learned from that, eventually the ultimate goal being to release a model that is completely fluent in scientific text and images, videos, whatever the case may be. So a lot of this will ultimately depend on the results and what we learn in these first 2 years. But that's kind of the larger picture and where we hope to go in the coming years. So how does all of this actually happen in practice? So the basic idea, or the first thing that you need to do really in order to train a large language model is collect a large amount of data. So in this first instance, we're planning on focusing primarily on text-based data. And so that requires aggregating text data from multiple different sources. So this text might be a bit small. Maybe hopefully people can read. Here on the left, it's essentially just 4 different boxes that have different categories from where we expect to take input data. So portion of it will be scientific or engineering structured data, things like vector fields, graphs that are common in engineering, as well as general text, media. So these are kind of the more typical text-based data that people are probably familiar with. So anything scraped off of the internet, archives, scientific journals are also an increasingly large part of these pre-training data sets. So specifically, there was a data set released from the Allen AI Institute called DOLMA that did a nice job of deduplicating, cleaning, and kind of aggregating some of the most popular sources of text-based data on the internet. So this DOLMA data set, which is what we are using to pre-train AuroraGPT, consists of aggregated tokens from the Common Crawl, C4, the Stack, Project Gutenberg, Wikipedia, and Wikibooks, and is just really an amalgamation of all of these different web-based text data sets. As well, and then, so that is kind of the more generic text-based data that you typically associate with large language models. In addition to that, we also plan to target data from many of these different scientific domains, so math, biology, material science, so on and so on. And really being able to incorporate these new modalities of data in a meaningful way is very much an active challenge. Eventually, this data is all aggregated and neatly packaged into a nice pipeline that we can then use to train our large language model. So given the input data, training on Aurora, enough time and maybe a bit of magic, eventually we will output this AuroraGPT fully pre-trained large language model, which will then be delivered to downstream teams and released publicly for teams and other users to do with as they see fit. So we expect that users will fine-tune and adapt this initial release on downstream scientific tasks. So some examples we have listed here are scientific discovery. Digital twins is a common approach in earth science and climate modeling. Large language models are being used for inverse design, even code optimization and generation. And so with the initial release of this initial pre-trained model, it'll then be released publicly and distributed with an open source license so that everybody can build off of it and adapt it to their specific use case. So what do we hope to produce as part of this project? So as much it is a learning experience as much as anything else. So as we've been working on this project, we've learned a lot about what it takes to actually train and scale these large language models. So I'm sure people might have heard before that these things take, many months of continuous training on thousands of GPUs frequently. And so it's hard maybe until you're actually doing it to get a scale of how large and time consuming that is and how frequently things break and how challenging it is to really have a large, sustained, distributed run on a supercomputing system, especially when you're competing with other users for resources. And so we've learned a lot from this, and going forward, we hope to turn what we've learned into these deliverable outcomes. So in particular, we hope to deliver data sets and data pipelines. So everything that we've used for the initial pre-training phase, all of the pre-processing pipelines for ingesting tokens, efficiently tokenizing input data from new sources will all be, it is all publicly released right now, but once it's a bit more polished up, there will probably be a more cohesive release. But all of this software that we're using right now to pre-train this model is available on GitHub and is publicly available. There's a link actually right here. So it's under the Argonne ALCF organization at this repository called Megatron DeepSpeed. If people are interested to look and see how it actually works behind the scenes. And so a framework that can reproducibly train these large language models that is open source, accessible, and as well as accelerator agnostic. So one of the major challenges we've faced as we have been doing this on the Aurora GPUs is that Aurora being an Intel system and having Intel-based GPUs, the existing software for large-scale distributed training is maybe not as developed or well-maintained as some of the software that exists for NVIDIA systems. So in particular, NVIDIA maintains this repository called Megatron that has evolved to be quite CUDA specific and not, without major modifications, is pretty locked into NVIDIA hardware. And so one of the challenges that we faced is we wanted to take a lot of the features that existed in NVIDIA's Megatron library, but we wanted to run them on Intel GPUs. And so previously, there was no straightforward mechanism for doing that. And so that required a lot of effort on our end to pull in features that we wanted to use from NVIDIA's CUDA-specific Megatron into a framework that is GPU agnostic. So it runs on Intel GPUs, Polaris GPUs, AMD, and we've actually scaled up to a pretty large number of GPUs on Frontier. And so it is nice that we have a framework now that is completely agnostic and runs on at least the 3 major hardware GPU providers. So it runs on AMD, Intel, and NVIDIA. But it took a pretty non-significant amount of work to get there. And yeah, so if people are more interested, the code is all available online. And I'd be happy to talk more about the details, internals of it, if people are interested. So that will be another major thing that we hope to produce from this, a publicly available, usable framework that runs on any GPU. We also hope to get a better understanding of how this approach of augmenting text data that is generically grabbed from the web, when that is kind of augmented with scientific data, how does that impact model performance? How can it be used to extract new scientific insights and so on? And a lot of this is just unknown. So it'll take us actually going through it and doing it and figuring this out to, have a better understanding of these types of things. Additionally, we also obviously plan to release the full pre-trained model weights. So similar to like Meta releases the llama weights, we plan to have all of this publicly released on Hugging Face once it's fully trained, which is where we are at the moment. And yeah, so there's a bunch of other things here specifically. So the promotion of responsible AI best practices is another actually pretty important point here. So safety in AI, and especially safety related to large language model development, is, I would say, a very important component of this larger project. And so we have been doing our best to try to incorporate responsible AI practices wherever we can. And we have a whole series of different teams that are looking at investigating specifically safety features and how to best enforce safety policies. So this next slide is on the details of Aurora. So I don't know, some of this is probably, sure, please. And yeah, so sure. Sure. So the question was, given these very large models with billions of parameters, how do you kind of find the optimal settings, find a good jumping off point from where you can then optimize further? So that's a good question. And so there are a lot of like auto hyperparameter tuning libraries that exist. So DeepHyper is one that was actually developed here that is a hyperparameter optimization library that takes in a global possibility of available options and tries to use some Bayesian search or some sort of method for finding an ideal set of parameters. And that works. Hyperparameter optimization approaches are relatively straightforward when your search space is somewhat constrained, but when you're dealing with billions of knobs to tune, it becomes a bit more difficult. And so we essentially started with the Llama 3 architecture and made variations on it that seemed fitting to the specifics of the Aurora hardware. So there are some details about some artifacts in the Llama model architecture that are various like layer sizes and numbers of layers had to be slightly adjusted to be divisible by factors of 6, for example, instead of factors of 4 or factors of 2, or other powers of 4. And so kind of, I wish I could say we had a more well thought out, carefully constructed way of doing it, but maybe Vaino can correct me, but I would say a lot of it is actually just kind of trial and error. You have some idea that if I change this knob this one way, I can expect some performance, and maybe I over dial it and you see that you kind of overcompensate on the other end. And so a lot of it is trial and error. We have some kind of rough idea about where to start looking, and then things are kind of, slightly adjusted from there. But even starting from the Llama 3 architecture, for example, might not be the ideal solution. It's kind of, you just kind of got to start somewhere, and then you can make improvements on it from there. And I'm sure there are many more optimizations and improvements that could be, with infinite time and resources, we could spend all day figuring out what the optimal set of hyperparameters is. But at some point, you kind of gotta say, this is better than anything I'd seen so far, and let's run with it, I guess.
So I see four model sizes here on the website.
Sure.
So do you continuously train those, or you?
So at the moment, we are focusing primarily on this initial 7 billion parameter model. Had we started all of them had we started the training for all of them at the same time, we've learned as we've been training this 7 billion parameter model, things that were wrong. So say we had to, restart at some point, or, something was wrong with this initial configuration, we had to completely restart. And so we've learned a lot from these experiences that had we started all of them at the same time, we would have had to have redone all of them. And so the plan and kind of the bigger idea, start small, make sure we have a very good detailed understanding of what kind of performance we can expect, ensuring that our mechanisms for avoiding catastrophic loss spikes during training is robust, and really trying to be as confident as we can be in the initial smaller model training run. And then from there, hopefully take that and scale it up to larger models where, there's less kind of room for mistakes and things.
Yeah,
Sure.
these prescriptions are in the Llama paper as well.
Yes,
So it's not like we're inventing something new. We're going with something that works, and we're following those kind of principles.
Yeah, you're getting your data from the internet. So ChatGPT and some of the models are also getting the data from the internet. And the scientific content, data of scientific content is a much smaller set than everything that's out there on the internet. So you would think that ChatGPT or Llama 3, whatever model you're talking about, already should have included the scientific content, right? So what are you doing that ChatGPT and Llama 3 cannot do?
Sure. So, the relative fraction of high quality scientific data that exists, it is dwarfed in comparison to the amount of generic internet text slop that is out there. And so one thing that I think probably that OpenAI and Meta and all of these other companies that are actively working on scientific assistant type models, one thing that they are very actively investigating is how best to try to mix some small amount of high quality data into a much larger, lower quality data set, and when exactly to do that in the training pipeline, whether you continually mix it in throughout the duration of the initial training, whether you try to stick it in at the end when it's already been pre-trained and kind of do it as more of a fine-tuning experiment. I think that some of these questions are still, I would say not answered definitively. And so finding the best ways to effectively mix in scientific data into these larger text-based data sets. Even just the access and where you get that scientific data from can play a large role. So one thing we do know is that high quality data is very impactful in during the training procedure. And so one thing that having access to data that other people might not is one thing that would differentiate somebody who is trying to train a large language model. And having some of the power of the federal government behind us, I think, has helped us to make some inroads into these types of things. So we have a lot of ongoing discussions with things like the Library of Congress and some of these other, maybe maybe out of the box data locations that we hope to be able to incorporate and meaningfully incorporate into our large language models. So I don't want to say definitively that we have a better answer than OpenAI does, for example, because a lot of it still remains to be seen. but at least we will publicly disclose what we find out. And so everything that comes out of this will be publicly released, which is not always the case for some of these more consumer-based companies. Yep.
Yeah, and Sam touched on this, right? So we're exploring some of these techniques like continual pre-training, like what's the best approach to do continual pre-training, or whether we should just go straight to fine-tuning with these high-quality data sets. So these are answers or questions that have answers remaining to be seen, so.
One of them is, so when do you decide that a model is trained? So do you have benchmarks?
So yeah, that's another good question. So like these one of the maybe surprising insights from some of these recent Llama releases is that they saw that their model continued going from, I think it was like the initial 2 trillion up to 15 trillion tokens. Their model was still continuing to improve, which makes it then very hard to say when is it done? When do you cut that off? And so we have an initial goal to pre-train on the 2 trillion tokens that comprise the Dolma data set as kind of an initial, once we get there, then we can maybe have a but you're right. It's kind of arbitrary in that sense. And what you ultimately qualify as pre-training versus fine-tuning and all of that kind of becomes a bit blurry when you get into the specifics.
Thanks. So one more question
Sure.
is, okay, so basically in many factual data sets, it's facts, like, okay, there is, I mean, of course you can find data sets in text as well where there are biases and things like that. But in scientific data sets, some of it is fact, some of it is biases. Like, how do you, I mean, all papers are going to tell that we are doing the best.
Yeah.
So how are you going to distinguish what is state of the art, what is not, what works and what doesn't? So
Yeah, so that is a very good question.
Yeah, we have another team that's working on that kind of curating the content. Sam's not involved with that team, so.
And so that was exactly what I was going to say, is that is an excellent question. And to the and yes, as Nathan said, we have a completely separate team whose primary focus is on turning scientific data into a form that factual based information comes out naturally and that can be structured in such a way that the model is able to learn something from it. Because yeah, like you said, it's not, researchers, tend to, exaggerate and tend to, talk about their own work, which, it's hard to try to extract a single source of truth, even from scientific data. And so being able to reframe it in a way that makes that apparent, or that the model is able to take something away from it, is the focus of the data and is the focus of that data team. And I don't know if any of them are here to talk to you more. But if you, I can. Yeah.
Thanks. So I think recently the Open Source Initiative just released like their first stab at a definition for open source AI, given that the term was thrown around a lot before, right? For open weight models like Llama, even though they don't release data. Just wanted to confirm if like you all plan to like kind of comply with that definition. It sounds like it's the case.
So I don't want to say anything definitively, because those decisions are going to ultimately be made by people well above me. As far as I am aware and have been told, we plan to release completely open source model weight, various checkpoints during the training, logs. Whether or not the ultimate decision on that is a bit out of my hands, but given where we are right now, and given that everything is publicly available, publicly hosted on GitHub, I expect that to continue, and I expect everything to be released completely, fully open source. But yeah.
Yeah, I mean, a quick follow-up question. Is there like any potential plans for like maybe have like an internal version of the model? Like say if you have like sensitive confidential data that you want to train it on and you potentially can't release?
Yes, so that is a very good question that I know Argon's team of lawyers and DOE, people are, because I think that is where specifically you draw boundaries and those types of things is, it's kind of being shaken out as we speak. And ultimately decisions that I don't have much control over. And so,
Yeah, it's definitely something that we're thinking about here, but not necessarily in our team. So the other. like
yes,
Sam is
there are
saying,
definitely,
these are thoughts though. We already, have been thinking about, okay, well, maybe some scientific projects might have some like data confidentiality kind of things going on, so they don't really want their data being, shared or stored. So yes, these are some of the things that some of the API teams or maybe some of the other teams are thinking about. So yeah, that's a good question. Good question.
So we've been talking about gathering the data, right? And you've said that you take data from scientific papers. Are those papers open access? If they are not, then how do the journals feel about the model being public? Because you said that model will be public. So, those papers will be available to the public indirectly, right?
Yeah, so that's, again, a very good question. The answer ultimately is going to depend, I think, on, very specific text and some final agreement that will ultimately get signed by people that are not me.
Yeah, as far as I'm aware, the high quality training data set that we're developing is open access or we've sent
will have
out like
permission
we've canvassed some select individuals in order to collect papers and stuff. So hopefully that answers your question. But again, we're not lawyers here, so we don't have the answers to these kind of questions, so. Anyway, so I think somebody had a question over here.
Maybe I answered it.
Maybe. Let's
Well,
continue.
if it comes back to you, raise your hand.
Oh, we got one here.
Sorry.
So how do you calculate parameters? Is it attention layers or layers and a mix of input data?
So you mean total number of parameters when we call it 7 billion, for example? So that is so for the pure transformer model, so it's the total number of active parameters in the model.
Yeah, we use the same calculation that's
Yeah.
described in the Llama paper.
Yeah. Good questions, though. Keep them coming. Oh.
So just for as a concrete example, for example, do you know if all of the manuscripts from OSTI from the DOE work are included in that data set?
So they are not included in the data set that will be used for the initial pre-training, I can say pretty confidently. There are all sorts of access agreements and how to get it and so on. And I think the details, I'm not entirely clear on the details of that, but as far as I'm aware, that is separate from the data that is being used for the initial pre-training, which will be what is used for the initial release, as far as I'm aware. But again, I wish I had more details on the data specifics. It seems like that's a hot topic. I apologize. Sure. Then we'll come back over here.
What is the main use of this? Can you give me an example of the optimal use case for this model?
So I think in theory, you could imagine you have some large language model, some model that has been very effectively trained on scientific data, and say you are a material scientist and you are looking for, I don't know, have some idea for some, some material property, what materials exist out there that have a melting point between temperature X and temperature Y at this pressure. What are some other useful features about that specific material? You can even imagine things like, so that was an example that somebody gave me specifically a while ago.
So it's kind of a database for published data?
Maybe that's not the best. So maybe that's not necessarily the best example, right? Because you could imagine things like that you might be able to just find in some lookup table. So I'm sure there are many more examples that I am not going to be able to come up with, but I think to some extent the use cases and how it will actually be utilized in practice will in some ways kind of depend on the model quality, right? If it turns out that we somehow produce this model that is beats all of the other models at math competitions or something, for example, then it would be very clear that that would be a model that's useful in for math research or something. And so I think a lot of how it will eventually end up being used will depend a lot on what comes out of this actually. And yeah, I know a lot of teams that are focused specifically on how to adopt and modify an existing generative pre-trained transformer to science-specific tasks. And so there's a lot of work even being done right now. The obvious example that should have came to mind is using these for protein sequences and using large language models that have been pre-trained on sequence-based data to generate new sequences. So specifically in the case of drug design is one area that comes immediately to mind. So having these generative pre-trained transformers that work effectively on genomic data that are able to generate new proteins is, I would say actually probably one of the most concrete examples of directly working with sequence-based data for a scientific application. That's true. So you're not wrong. And so I think if we knew right now how it would be best used, then we would design specifically for that use case. But I think a lot of how, what benefits it will have will ultimately come out of, how it performs on different, domain-specific tasks and so on.
Yeah, and we're really early in the stages of training AuroraGPT and of the project in general. So if you have any good ideas about potential use cases, especially in the scientific domain, please don't hesitate to tell us, especially in the chat. It'll be good to hear your thoughts on this.
And I'm sure when I walk out of this room, 5 examples will come right to my head. But
to train these models on LCF clusters, you probably need a lot of customizations, like how to load data efficiently from parallel file system, SSDs, checkpoints, and stuff like this. Is it all published on your repository?
Yeah. So that's a very good question. There are a lot of details and internal work, even just to get things functioning correctly. There are so many pieces. There are so many different parts that all need to work together correctly in order for all of this to succeed. And so there's been a lot of work. And if you go to the GitHub repo and see all 2,000 or so commits over the last year that we've made to, get it to the state where it is today versus where it was when we started. So, all of the changes and everything that we've done over the past year and a half are all publicly in that GitHub repo. The one maybe other slide I will get to, one thing that we did in particular. So as we were beginning to run experiments with this large language model and really using the full data set like we anticipate using for the actual pre-training run, we found that using the existing software, when trying to use this full 2 trillion token data set, at the beginning of every new training run, it took about an hour or so to do this index creation that gets ran at the beginning of every training run. So it's basically this index creation process where each batch of training data gets mapped to where it is on the individual file system. So if I want to train for 2 trillion tokens, I need to explicitly map out ahead of time where each batch of training tokens is going to come from. And so this is this like index creation process that happens. So it's only a one-time cost. So it happens at the beginning of training and then it's cached. And then when you load in that model again, it will reuse that data that it had already calculated it for. But then when you want to try a new experiment, so when you want to try a new set of hyperparameters, for example, or try a change to something else, for example, you would then have to work through this entire hour-long process every time you wanted to try to do a new experiment or try a new configuration. So we very quickly found this to be prohibitively expensive when trying to actually make progress and run experiments. And so the reason for this was because the existing implementation was designed to run basically in sequence. So it would essentially work through each batch of data sequentially on a single GPU, which ended up taking about, I don't know, over an hour for typical use cases. And so what Huiho did, who is here somewhere, spent a lot of time and actually, there he is, did an amazing job actually and completely got rid of this initial overhead by essentially distributing this bin and index creation over all of the available workers and running that in parallel instead of sequentially on a single worker. That got this initial bin and index creation time down from about 60 minutes to under 4 minutes, which makes it much easier then to try a new experiment. And so this was another one of those kinds of things that the existing implementation, it worked well enough, but didn't work for our use case. And so actually took a pretty non-trivial amount of engineering to get it working correctly and to the point where we wanted it to be.
Yeah, and there's still a lot of like in-house knowledge that we're still working on distilling down. And as Sam has said many times, we plan on making all of this public.
Thanks. So let's assume you're done with training and you have a beautiful model. Will that be deployed here or somewhere else, or?
That's it. So another very active conversation we are having is within the larger ALCF department is how best to try to deploy these types of models. So specifically for the case of AuroraGPT would be our model, but more generally how to stand up or provide a system that is able to serve these models to users on a more reliable, consistent basis than we've come to expect with supercomputing clusters, where they go down for maintenance every other week, or this and that and the other. And having a system that is has 99.9% uptime, that is reliable, always on demand, that can be accessed without having to wait in a queue, and how to stand something like that up in a way that we can then provide that service to our users. So there's a whole team dedicated exactly to that. So there is the inference team, Rajiv, and there's a whole bunch of other people that work on it as well. But that is very actively working on that question specifically. And so I expect that we will have a service or a mechanism for deploying it and serving it out from ALCF directly. But with the model being released publicly as well, it is open to whoever would want to serve it, or however you could run it. Hopefully, that quantization library, Krishna, will have a quantized model up, and you can run it on your CPU later that day, in theory. But
when you release these models, what are your thoughts on interoperability with NVIDIA and NeMo? They've done quite a bit of work with even BioNeMo framework for drug discovery. So
yes, so we have an active relationship with the NVIDIA team that's working on their Megatron core and NeMo specifically. And it's a good question. So it's the tensor runtime, the increasing dependency on the tensor runtime library in NVIDIA machine learning libraries makes it increasingly hard to generalize them to different hardware. And so as long as a major component of NVIDIA's software stack relies on tensor runtime, it will be very difficult to, yeah,
I think the answer to the question is our next machine is an Intel-based machine, so it makes these kind of portability issues, something that's kind of out of our hands.
Yeah.
So I don't know, we're running a little low on time. I don't know if you wanted to say anything about like maybe NAIR or FAST, or if you had anything else you wanted to.
So the one thing, yes, I would like to say. So yes, FAST is a large DOE initiative that is, can't remember the acronym, but is going to be a large source of funding in coming years, specifically for large language model and these large model development efforts, which, excellent, thank you for reminding me, brings me back to this slide. So this afternoon session, I believe, is going to be covering in more detail the specifics of the AI test bed that we provide here at ALCF. And so just to maybe briefly mention, these systems are in production and available for allocation. And I know Sid will talk to you more about that this afternoon. There's also this NAIR pilot, which again is another National Artificial Intelligence Research Resource pilot. And so these are, large kind of, top-down decrees prioritizing large language model and large generative modeling development in the workforce and resources. And so I expect these things to only grow in coming years, especially as, we get more funding, so. And I think that was all I really wanted to say. So here's a bit about some of the different teams. This I just said out loud, and I said yesterday as well. So as people can imagine, it is painstakingly difficult to get this all orchestrated and working correctly and efficiently. And it has been a major effort from everybody. So I'm up here talking about it right now, but Nathan, Huiho, Varuni, Vaino, Venkat, who is around here somewhere. This is a very large team effort, and it would never have been possible without everybody else. Everybody, Rinku, everybody, it's been a very collaborative effort, and so a lot of people have really contributed to make this, to get things where they are today. And so that's about the time. Yeah, I think that's it. If anybody else has any other questions, feel free to reach out. Otherwise, I'll wrap it up there.
Thanks a lot, Sam.